So, should be recording. Good, excellent. So, I'm glad that you're all here. I feel like I barely showed up. I was in another meeting until just right before this one, and it was the dean talking about the budget to individual departments, and today was his day to visit our department. So, there were a bunch of questions, and of course, all the best questions are at the very end. So, I felt like I couldn't leave, and now I'm here running a little bit late. But I feel a little scattered, but that's okay. Probably you do in your life too. How many of you felt like in every single class this term you've been like on top of it and everything's been just perfect like normal? Like four of you are shaking your head saying no, and the rest of you are internally. Harrison's like, yeah, everything's cool. Okay, so fine. So you're all understanding where I'm coming from. That doesn't mean you forgive me for my errors, but that's a different issue. And at one level, I care, but at another level, I can only do what I can do, which is what I expect of you guys. Do your best, and then we'll see what happens. Okay, so let's start with any questions about administrative things that you might have. And then maybe I'll remind you of a couple things, announcements by the way, and then questions about administrative things. Then we'll dive into questions you have from subject matter from the recent past, and then dive into class today. And if you noticed, there is no lab for the day. It's because I've tried for years to write a lab, which is really perfect to be dealing with this other pair of topics in Chapter 7, the interaction between quantitative variables and each other, or self-interactions. And really, I find that that's best to put off by about 1 to 2 weeks, depending on the situation. There's another key topic that when we consider it first, it makes, I think, better sense as putting part of Chapter 7, the lab portion of the other parts of Chapter 7 a little bit later. So the the announcement really is there's this test coming up. It covers through Chapter 7. We're going to go and in a lecture content, in a lecture format today, finish up what we can from Chapter 7, and then we'll start in on Chapters 8 and 9 next time. 8 and 9 are not related to your exam. But if we do get forward into Chapters 8 and 9, the material in 8 and 9 leans so heavily on the material in Chapters 6 and 7 that it reinforces your understanding of the material that is covered on the exam. The exam should be available online by Saturday, turn it in by Tuesday, and that's good. I will have a lab for you possibly next time, but I have the feeling you'll probably want to instead spend time talking about a sample exam. Okay? So I'll have a sample exam next time, or I guess I'll put it up later today, and then we could talk about it next time in class. But if we don't have enough time for, well, if you don't want to use the time for that purpose, we'll do the lab on Chapters 8 and 9. Okay? So that's my sort of announcement sort of stuff. How about questions related to administrative matters first? Anyone? It's almost like you've been in school before and you know stuff, like how to read a syllabus. Okay, well, if any are questions, don't hesitate to send them to me via email or put them in a discussion somewhere. Okay? How about questions about subject matter things from what we dealt with last time, which was the interaction between a categorical variable and a quantitative variable? So that's a big old no, not yet. Fine. Interrupt me partway through if you want to. What I want to do is to sort of start up then with content related to, again, interactions. That's what we tackle and emphasize in Chapter 7. But emphasizing interactions between quantitative variables. And I was thinking, can I write up a lab? And I sort of got partway through an analysis earlier today, which I could have written into a lab, but then we hit the department meeting and I thought there's way too much content for the background. So we'll present the one example in class in great detail. And then if you'd like to ask me to do another example, I could talk essentially my way through the sort of data set that would have formed the second example. I'll have as a second example the data set that would have formed a lab if I had been able to successfully complete one, an additional lab, that is. So let's say screen share, that one, go. Okay, so what we do know so far is essentially if you have two separate variables that are explanatory variables, they come into to life as quantitative or categorical. And we started with categorical and categorical interaction with the pig diet example. Okay, so we already saw that. We also talked about that in the context of my commute time to campus. And yeah, the impact of the route that I take on the time to campus depends on the time of day. So that's categorical. Then we considered a quantitative categorical interaction, and that's where you emphasized in the lab last time the three different types of careers and their relationship, the way that career type impacts the relationship between income and prestige. Okay, so that's Duncan's data, like we already talked about. And in the same data set in the Chapter 6 lab, you realize, hey, there's three separate groups. We need three separate trend lines, one for the blue collar, one for the white collar, and then one for the professional. Three separate trend lines for the three separate categories. Okay, so you fit that, you were happy. You could even calculate an equation for what is the intercept and what's the slope for each of those 1, 2, 3 trend lines. And you found in Chapter 6, without an interaction, those three separate trend lines are parallel to each other. In the Chapter 7 variant, when you included an interaction between income and then type of career, it allowed for the slopes to be different across the three different career types. You probably found, though, that the interaction was not statistically significant. So you said, there is no evidence that the slopes are different across the 1, 2, 3 categories. They may have been different in some greater population, but the data you have didn't convince you that there is a different slope for blue collar and professional and white collar. Perhaps there's only two separate categories, maybe there's three. You just said you didn't see a difference in the slopes across the three different groups. So let's move forward in the context of a different example, okay? And in this example, where did I hide the data? Well, I've got this version here. Darn it, where did I? Oh man. When you hide data on the screen and then move it around, it disappears. So I just open it again and it's really the same data set. These are data that I may have mentioned already, okay? And the notion that we have here is perhaps that the yield of corn, and this is in bushels per acre in one particular county in Illinois, that changes across the years. 1890, there was 24.5 bushels per acre, and by the time we hit 1927, it was 32.6 bushels per acre. of corn. Okay, so you think maybe across time there is a time trend that indeed across the years, perhaps agricultural progress should get you a higher yield, but also we're sort of aware that rainfall should play a role as well. If you get no rain at all, you'll have a very different yield than if you have a moderate or the right amount of rain. And if you have perhaps too much rain, it's going to impact the corn in a very negative way. Okay, those of you who in crops may very well know that, or some plant sort of people probably know that really well. If the plants are sitting in water but they're not used to or designed to sit in water, they might essentially, what do you call that, be unable to breathe. And so they'll die. Okay? So the question that I have is, what is the relationship between these two explanatory variables, year and rainfall, and then the yield in terms of bushels per acre? So one way I could do that is to explore it, and I'm going to go with Graph Builder for now. And it's a convenient way of trying to take a three-dimensional relationship and compress it down into 2 dimensions. Yield, I think naturally it may depend on the year. Let's turn that wiggly line off. I see a positive trend. As years go by, the yield goes up. I could also say, well, maybe, shoot, the rainfall level. As the rainfall level goes from 6 to about 12 inches of rain for the year in that county, we see the yield is certainly increasing, and then it seems like it maybe levels off or starts to drop again. Those are fair statements. Well, if that's my graph here, that yield may depend on the rainfall level, and that makes a lot of sense. Why not include the information about what year it is as well? Now, maybe I should highlight this in such a way that I can see more cleanly. Okay, so what I just did, in case you aren't picking up on a few of these tricks that I haven't explained so far, and I apologize for not doing that as clearly in all cases. I had one row highlighted, and because of that, one row was in a darker color, and all the others were sort of grayed out, and that makes it challenging to read. So if you click up here, it will remove, say, the highlighting of one particular row, like 1891 right there. But if I click here, it sort of says all colors will be displayed at their fullest depth. So as we go from early blue to late red, I see what looks like a positive trend early on in the blue, yes? And later on in red, I see the red ones are sort of flat or maybe even negative if you call that very low yield at a 14-inch rainfall. Maybe it's a negative trend. And in the middling range, sort of bluish gray and reddish gray, it seems as though it's still positive, but not quite as steep as just the blues. I think it's fair to say that across the different years, there's a different slope relating the rainfall level to the yield. That's what the picture is showing me. Question?
There's just some people commenting in the chat that the graph that you're sharing with us is just kind of distorted, I think, when you were moving things around.
True. I'm seeing that on my iPad. So let's drag it over here and bring it back. Thank you. So I'm not paying attention to the chat, and if like that I don't spot what you're all saying or want to be saying, maybe I should even turn the chat on. Boom. Definitely draw my attention to it. And I apologize for errors on the part of my computer, but that one was beyond my control. So now can you see blue steep, red flat, gray somewhere in between? Okay. If I have a regression with 2 explanatory variables, we've already touched on or talked about how essentially what you have is an XY relationship, but with 2 X's, one direction And another second direction, that third direction is, if you will, up. So let's create some space, and let's draw the picture again. If I were to show you graphically the way I imagine these things being displayed in 3 dimensions is y is up, x1 and x2. If we were sitting in a classroom, a regular classroom with desks, rows, and columns, if you will, you could view x1 as corresponding to what row number you are as you head from the front of the room towards the back. Row 1 is quite close with the low numbers, row 2, 3, 4, row 1, 2, 3, 4, something like that. Maybe let's get a big classroom with 5 rows, big for Cal Poly. Even 6 rows. Sure, let's do that. And then the columns as you head from the door towards the window. Now, when I say door towards the window, you know what I mean, but that description works nicely for the doors that are in the front, right near the chalkboard or whiteboard. I don't know what room you're imagining, but you've all seen classrooms, right? Rows and columns. Now, does everyone have an individual nose in the classroom? Imagine the y value is the height of a person's nose in the room. Now, the person in this upper right corner may have their nose here, and then I have a collection of individual noses. The heights, okay, this is the height of the nose. Here is the row number, and then the column number, or if you will, how many columns over from the door you are. Now, that's all of a sudden a mess of a graph. And there is no way to take any 3-dimensional object and project it onto a 2-dimensional space without linear algebra, but I'm going to attempt to draw that generic picture that we like to do in sort of the mathematical disciplines. We could show you essentially where the y is for any given value of x1 and x2. If I drew a plane, okay, you're saying it's linear in each x1 and x2. So again, as x2 remains fixed, we're talking about the people closest to the window. As I go from the front to the back, the students don't tend to get a lot taller, but actually a little bit in most classes. Taller students tend to sit a little bit more towards the back. I think the reason is because the shorter students really benefit from being up front rather than sitting behind the tall people. Okay, so the shorter students either sort of sit towards the front naturally, or the taller students say, I would like to defer to the shorter students so that way they don't get their view of the board blocked. Okay, so we see a slight slope. So the slope is upwards like that. And as you head from the door towards the window, so door, window, we see in this case it looks like a negative slope for a 1 column over as you go from the second row over from the door to the third row over from the door. The students are a little bit shorter, their noses, maybe they slouch, I don't know what the hell, okay? Can you imagine 3-dimensional space, but I'm showing you in 2 dimensions? Okay, flat plane, multiple regression, 2 x's. If you got 3 x's or 4 x's or 5 x's, it just gets to become a hyperplane. It's harder to draw. But any 2x values and then the corresponding y, at least the 3-dimension into 2-dimension thing can be approximately described. Okay? So if there is no interaction, it's a flat plane. Let's change things to allow for an interaction. An interaction essentially will be bending the plane so that way in any one direction we still have linear. For one x fixed, the other has a linear relationship with y. Okay, so that's again what I'm going to attempt to draw. So let's go with black again for the axes. Here's y, here's x1 and x2, and I think I had x1 here and x2 there. Now I'm imagining, and again, I'm going to use terms like window, door, front, and back, because I think it helps students grab onto the orientation here. So here's the door, D for door, W for window, F for front, and B for back. Now imagine we have in the very left row, from my point of view, facing y'all from the front. Can you see why this lecture goes a whole lot better when you're actually sitting in rows and columns? Yeah, sorry about that, dudes. Okay, so the person in the front left corner is in the front row near the door. If he is extremely short, I'm thinking very short. But if in the very back we have a very tall person, that's a positive slope. What if in the other side of the room, the side near the window, it's a tall person in the front and a very short person in the back? I would think that sort of picture describes what's going on. As I go from left to right, on the left, from the front, I see the short people in the front, tall in the back. On the right, I see the tall people in the front, the short in the back. If I were to say, aha, there is a bending of the plane, you might be able to say, oh, I can see that plane looks bent. Now, again, I apologize for a two-dimensional projection onto your screen here, but imagine this. Literally the people in the, and I ask students to stand up, in the left-hand row, in the very back, could you stand up, please? And in the right on the front, I ask them to also stand up. What's the best fitting picture that goes along with that? You could say, oh, look, it's a bent plane. I'm going to take the plane and I'm going to bend it like this. Again, if you're looking at me, great. If you're not looking at me, well, you can watch the video later. I'm going to take that front right and push it up, the rear left and push it up, the front left and push it down, the rear right and push it down. I'm taking that flat plane and I'm going to bend it like that. Okay? I'm taking my plane and I'm bending it. Now, great, I did geometry, yippee skippy. Let's try this with corn yield and rainfall. And then we'll see how our friend, the profiler, actually helps us understand what's going on. Okay, there we go. The yield can depend on the year because technology over time could increase the yields. And also, I'd like to think that the rainfall level impacts the amount of corn you get. Okay, under my model, my initial model, my model 2, I guess I should say, where yield depends on rainfall and year, but no interaction, I would say the yield depends on the year, boom, and the rainfall level. I could put them in the other order. It really wouldn't matter. It's going to fit the same exact plane. I get my same R squared. My analysis output here tells me, well, tells me lots of stuff, but I want to focus in on the things that will help us understand better as we try to fancy it up with the interaction. Without the interaction, with the additive model, if you will, where the two terms are added together, not multiplied with an interaction, we're able to explain 30% of the variability. And with my effects test, I'd say, yes, controlling for the effect of rainfall, I see a trend across the years. If I fit a linear trend, I'd say it's statistically noticeable. And controlling for a possible linear trend across the years, there's definitely a rainfall relationship, again, that I'm fitting with a linear pattern. I just fit this flat plane. Let's see if we do better with adding an interaction. Okay, so let's take our friend over here and redo the analysis under fit model. Recall that. And now I'm going to take rainfall level and year, highlight them simultaneously, and hit cross to add the interaction. I'm going to run that. And again, well, I'm going to have lots of stuff that I'm going to want to focus on, just the little bits that we're going to need for the sake of comparison. The first thing I want to do is see if R squared is better, and I think 48% is better than 30%. I'm able to explain almost half of the variability, whereas previously been less than a third. The variability in the yields can be explained considerably better with our model with the interaction. Okay. Under the ANOVA overall, it says at least one of our terms matters. The parameter estimates, which you could refer to as corresponding to the effects test, it tells us which are significant and in what way. The effects test is what I like to look at. Year rainfall interaction, highly statistically significant. Notice also, interestingly, that our earlier year impact, our slope earlier had been a 0.01 p-value. It's now cut by about 50%. We're able to more cleanly see the year relationship if I have the interaction. If you will, on average across the years, it's more noticeable now with the interaction than it previously had been. This p-value here for rainfall also a little bit reduced. Having the interaction definitely helps me in 3 separate ways. Cleaner understanding of the impact separately of year and rainfall, but then also it justifies itself. Any questions so far? And I'm going to say, I feel like I'm throwing a lot of content at you relative to the number of questions that are coming back. So I want to say, hey, any questions at this stage?
Yeah, I guess I have one. So when you're looking at the effects test and you see that the p-value for the year and rainfall together is low, that's when we already have accounted for them individually, correctly? Correct?
Are you referring to the 0.0072 and 0.0068?
Yes. Well, I guess I was saying that no, it'd be the 0.0014, so that it is significant, but that's after we've already taken into account them the year and rainfall individually, correct?
Correct. Using the adjusted sums and squares approach,
yeah,
having already included year and rainfall in the model, are we better off to take that flat plane and bend it? Heck yes, we are.
Yeah. So then where would we find if they if it was standalone without already taking into account year and rainfall?
Okay, well, I think it's a strange question to ask.
Right.
Is there an interaction between 2 variables if I don't at least control for those first?
Yeah. So
essentially, you're talking about something that is called model hierarchy, and we'll talk about that in great depth in Chapter 10. But the rule of thumb for now is, if you want to test a term like the interaction here, you need to have each of the separate terms in the model first.
All right. Yeah, makes sense. Thanks.
Okay, so let's look at this, what it actually means in the context of this analysis. And I think you might want to get used to, under factor profiling, looking at the profiler. If you have an interaction, the profiler will really clean up your ability to understand very much better than just looking at the numbers would. And that's one huge benefit of JMP over Minitab, okay? And that's one huge benefit of this course with JMP versus the textbook-only approach. So if I'm using the profiler, again, maybe I could get rid of a lot of this stuff here. That's good. And let's zoom in on what just this profiler wants to tell me. And I'm going to do that by making it larger so I can see. what's going on, I'm able to say that there is an effect of rainfall on the yield. Here in my right-hand graph, I can see the estimated relationship between rainfall and yield if it was 1908. We could also fix the level of year to be earlier, like 1890. In 1890, the impact of rainfall is quite steep. So we're saying in 1890, our data suggests that for each inch of rainfall, there's a huge increase in then the yield. If I were to go forward, sorry, let's grab this there. If I were to go forward a little bit to say 1900, it's shallower, but higher overall. Shallower, but higher. Higher overall, I think that could be attributed to the year, therefore, changes in technology, in crop science. This is sort of like the history of agricultural advancement lecture. Okay. If we go forward to 1910, it's even higher. Notice that as I do go from 1890 or 1885 to 1910, the overall trend line does get higher, but it also gets flatter, which is, I think, interesting in its own right. And I think eventually it gets to be what I would call noticeably flat, or not noticeably downward sloped, at least. Notice here that this horizontal line, dashy line, says, at least for 1925, I don't spot an overall negative trend. Even through the whole of the data set until 1930 or so, I don't spot the trend as necessarily negative. Early on, very much positive, then flat. Flat and higher. Steep, flat, but higher. Okay, so what could be going on here? And I know the history of crop science majors aren't necessarily in the room here. Wouldn't that be a cool major, the history of crop science?
Would be an improvements in irrigation.
Irrigation. There you go. This is a county in Illinois that was nearish to a river, but not so near that it was easy to get water into the fields in that county. So yeah, you could irrigate, but it involved pumping the water. And you think 1885, it's not probably a lot of pumps that could pull that off. By the time you end up in 1930 or so, yeah, everyone had a pump, or at least every community could afford a pump to get the water into irrigation ditches that then could be distributing water to all the farmers in the community. Irrigation itself is what's causing our trend line to change its slope. Another spin of that same concept is, early on, if you don't have enough rain, you don't get corn. Later on, you don't care as much if you have rain because you can irrigate. We had the access to the water to grow the plants. Okay, so I think that's sort of a clean explanation, and then it illustrates how you can use Prediction Profiler or the Profiler tool to make sense of what's going on. Okay, anyone want to ask a follow-up on this? Harrison, maybe?
Yeah. So I remember you said a second ago, like it was clearly positive and then it goes towards zero. But like to me, that looks like it's clearly negative at the very end.
Doesn't that look negative?
Yeah,
On the right?
Why are you saying it's zero?
Well, I'm saying the trend line drawn in here that's horizontal, the red one, in this margin of error of the actual population trend estimated by our model for rainfall in 1930, it is not noticeably differing from a zero slope. So no, a horizontal slope could actually make sense. So I'd say it's not noticeably negative in the same way that off to the earlier time period, that is definitely, oh, hold on. Bad. Okay. Oh. Okay, so recover. Okay, grab that one. Okay, so unlike, he says, continue this earlier sentence, unlike now in 1885, definitely a positive slope is I grab hopefully just the year and move it. I see no departure yet from negative, with a few more data points that were that would be high in terms of the rainfall level. If they were later on in the time series after 1927, you might actually spot the problem of having too much rain. But we'll change that thought in just a second. Okay, so I think we've done everything except for the algebra from the prediction expression or the prediction equation. And let me sort of walk you through the algebra of this, conceptually at least, and then we'll sort of move on and talk about a self-interaction or a quadratic. Okay? So, like previously, if you were to look at this parameter estimates set of slopes, if you will, we have year minus 1908.5 and rainfall minus 10.7842. That's a centered version of the model. In other words, 1908.5 is halfway through our year list of numbers. And 10.7842 is the average rainfall level. And because of reasons that okay, we'll just go over there. If I were to try to use the effects test and compare it to the sequential tests, if you have centered your data, if you have the data expressed in the form 1908.5 and rainfall minus 12.7, notice that my interaction test is the same, but also the effective rainfall is having a similar F ratio, as year has a similar F ratio to downstairs and also similar p-values. If I choose to not center algebraically, the interpretation of those parameter estimates would change and the effects test may be impacted. So I'd like to rerun it without the centering. And the reason is I'm going to eventually do some algebra. And to get there, let's just go ahead and fit model. Recall our old friend. Recall. Now, if I were to remember, okay, so make sure you do not have the center polynomials checked if you want the more convenient output for doing algebra yourself. Okay, so let's just verify. Yeah, I did deselect the center polynomial, so I'm good. Run. I do have, well, collection of output. I can't get rid of the things that bother me. Obsessive compulsive here. And go ahead there. Same R squared as before. 48. We earlier had under summary of fit 48 as my R squared, 48%. My analysis of variance, my model overall, my analysis of variance, same 10.6, same p-value. My parameter estimates, okay, that seems to be a little bit different than before. My parameter estimates now don't have the minus 1908.5 and the 10.78. And because of that, notice that my rainfall p-value is now different. And my year p-value is now different. Under effects tests, my F ratios are different than previous. When you don't center versus when you do center these interaction terms, the impact is that the meaning of the lower order terms is changed. Let's talk about why that's true for a moment. This is relative to the year being 1908. Suppose we're talking about a rainfall level that's either right at a 10.78 or 1 unit higher than 10.78, 11.78. What if we're talking about a 1 inch increase in rainfall from average? The slope here is 0.08. I'm sorry, I apologize. That's not the cleanest way of explaining that. Let's talk about just year by its. Okay, I want to bail out of that. And show you the picture as the same first, and then we'll do the algebra, and then we'll come back to that. Okay, so under factor profiling, the profiler does show us the same graph as before, and we can see as you go from early to late, we see the exact same everything. Same R squared, same SS error, same ANOVA overall, but the effects tests have been changed. The interaction term now has a different meaning because the slope for the interaction is now with a different impact. How do I phrase that? If you're standing at the average X, and you change the slope by 1 unit from the average, it has an impact on all of the predicted values, right? Again, 1 unit steeper slope changes all the predicted values. If you're standing at the very X equals 0 location and talk about a 1 unit increase in the slope, it changes all the predicted values quite differently. Again, if you're at the middle, changing the slope is changing the slope relative to the middle. If you're at the end, changing the slope by the same amount has a different impact on all the y hat values. Okay, so let's go ahead and try the algebraic exercise with my parameter estimates now. And these are parameter estimates, year itself relative to the year 0, and rainfall level relative to not having any rainfall at all. So let's go ahead and try it with our couple different potential years that we could look at. And I'm going to say, if the year were 1900, well, maybe I'll just write down the whole model itself. Y hat, the predicted rainfall levels, negative 2047, 0.0, plus then 1.085 times then year, plus then 168.27, and let's go with 272 times then the rainfall level. Now I'm going to subtract out, or I guess I'm going to add a negative 0.0878 times then the rainfall level times the year. Okay, so that's my base model. And like we had done previously, if I were to say, let's pick a couple fixed years, and for each of those fixed years, we could then calculate what the trend line is. So if it's 1890, the way I would pull that off is y hat is negative 2047.0 plus 1.05 or 08. I'm sorry, 1.08. Let's just go ahead and erase that mess. 1.0855 times then the rainfall level, or no, that's times year, 1890, plus then 168.272 times then the rainfall level, plus a negative 0.0878 times then 1890 times then the rainfall level. So I'm spotting in yellow things that don't have at all rainfall in it. And now in red, I've got what is multiplied by rainfall. So let's do our algebra here. And I think a calculator would be wonderful. If one of you has a calculator, I'd appreciate that. So let's go ahead and I'm going to write this out in blue. So what is negative 2047.0 plus 1.0855 times then the rainfall level, or I'm sorry, 1890. I want to know that number itself. And while one of you is doing that and then going to tell me the numeric value, I'm saying, look at this. This is how the intercept is adjusted for it being 1890.
4.595.
4.595. Okay, so I'm going to write that out. 4.595? 595. And let's just go ahead and move our friend over a little bit and move this other guy over. Okay, so 4.595. Now I'm going to add to that, well, the rainfall slope was 168.272. 168.272 minus 0.0878 times 1890. And that's all going to be multiplied by the rainfall level. Okay, so what is, well, we had, I guess, a slope of 168, which seems pretty steep. 168 is the increase in yield for a 1 unit increase in the rainfall level. But, you know, that's if it was the year zero. Because it's 1890, we have to adjust the slope downwards a bit. So what is this overall value here in blue?
The last equation is 2.33 times
2.
rain.
3. So 2.33 times rainfall. So I'm going to trust you on that. I'm happy to do that. If the answers are wrong, blame me for trusting you as a group, and that's fine. So we've got an intercept and a slope for the rainfall level. So here's a trend line for 1890, the 1890 trend line. Could I go ahead and redo that whole exercise for 1900? Or 1910? Or 1920? Our book walks you through exactly how to do that. Do y'all want me to do it right now for another year? He says, thinking, this is a great exercise, but I don't want to do it again. Okay, I'm seeing that as a group you're stipulating, yes, it can be done. Okay, but what I really want to emphasize here is the slope of rainfall was affected by the year. In 1890, the slope is decremented by 0.0878 times 1890. In 1900, the slope would go down by 0.0878 times 1900. 168.277 minus 0.0878 times 1920 would be what the slope is for in 1920. The interaction term, the interaction slope, if you will, is how much our actual slope is changing by because the year is 1890 or 1900 or 1927 even. Okay, so what we've got here is this nice pattern that explains how you can get to your downstairs friend, this prediction profiler. The prediction profiler does all that for you very easily. Okay, again, if you tell me the year, I can see what's going on impacting rainfall. And I don't even know what I did. I clearly did something goofy here, because that's for like a very different pattern. Okay, so any questions about that so far? Okay, so what did I want to do with that? Okay, so let's get back towards the lecture content and see what we want to finish up right now. Okay, so we've taken this interaction, bent the plane, and we can use the profile graph. Oh yeah, the other thing that I wanted to make sure I could show you is if you have the under estimates, the prediction expression, or the prediction equation, if you will, it just is those numbers you could copy down before you do the algebra, and you could plug in the year 1890 or 1900 or 1930 in each of those locations just to see what's going on. Okay? So that's with an interaction. What about a self-interaction? Okay, a self-interaction is what I think is not always the best way of saying a quadratic. But in a quadratic, the slope of the quadratic, for those of you who remember calculus, is different depending on the level of x. As you move from the very left to the right in a quadratic equation, the slope is going to be changing because the slope depends on x itself. I guess I should say the slope of the tangent line to the quadratic equation that we're sort of representing is going to be different based on the value of x itself. It's going to be found via calculus if you want. I'll just say if you have a self-interaction, and I'm going to suggest that that our initial model with rainfall and rainfall in the year could be altered differently to have rainfall squared in it. That's going to give us a bending of the rainfall relationship with yield. So let's go ahead and see if I can find my data set, which I moved over here. Okay, so again, losing on my screens what I had, so just open it one more time. Okay, so I've got here yield, year, and rainfall level, and if I were to emphasize the relationship between rainfall level and then the yield here, rainfall level along the x-axis, I can see what looks like, well, maybe let's make it, yeah, it looks sort of curved here. Okay. If I were to show you differently for the different years, again from early, I'm sorry, different yields, sorry. Let's put year here as the color. Okay, so we can see from 1890 blue, steep, to red, but if I had fit a curved pattern in each of those different time periods, here's how we could pull that off. And maybe I'm going to sort of start with just this graph. If I were looking at this graph relating rainfall to yield, even if I have different colors for the different years, I'm thinking curved. I'm going to fit a curve first. I'm then going to go ahead and add in year to the quadratic relationship between rainfall level and yield. And then I'm going to try and see what happens after that. Under Analyze Fit Model, we could see how the yield depends on the rainfall level. And if I fit just a trend line, a flat trend line by itself, I'm going to sort of tip my hat to chapter 8 here. You can spot that the residuals seem to have a curved pattern. The distance above or below the trend line seems like it's mostly negatives for low rainfall levels, and for high rainfall levels, the residuals are negative. In the middling range of rainfall, say 10 to 12, the residuals are mostly positive. The residuals being systematically predictable based on the knowledge of just the rainfall level says there's something that I'm missing in my analysis. My analysis that ignores the curvature should be fixed in some way. One way to fix curvature is to go ahead and fit a curvilinear model. How do we pull that one off? Recall the earlier friend, rainfall level. I guess I could take rainfall level and notice where it says macros and degree. I could say I would like a polynomial up to degree 2. That sounds like I'm going to have a quadratic. Rainfall level and rainfall level squared would both be in my model. I could have rainfall and rainfall level squared. If I were running that analysis by itself, I'm seeing a curve. Indeed, the analysis that JMP performs with Fit Model tends to produce the most reasonable graph at all possible up at the very top. You may have been frustrated with sometimes when you're doing something in JMP, the output by making a change to your model, the output looks dramatically different. It's because they're saying, well, you fit a different model. Here is the typical results that someone would want to look at with this version of the model you fit. I just fit a quadratic. It's showing me the quadratic I fit. Okay, so I've got a quadratic. I'm able to explain some 30%. Well, that's only a little bit better than before. When I had the straight line, I also did about 30%. When rainfall plus a year did about 30%, which is rainfall and the quadratic model, I'm able to explain some 30% of the variability. But in my analysis stage here, the effects test, again, these are terms that I think maybe should be tackled sequentially, because the more complex terms later on, we should control for the simpler terms. But I don't necessarily want to say something like controlling for a quadratic model with rainfall squared, is there a linear trend? I think it's a little bit more natural with a sequential test to say, is there even a trend at all for rainfall? Yes, there is. And if there is a linear trend that I fit, is it curved? Yes, I see a curve. Let's go ahead and look at now the model that I could fit if I had year in here as well. Again, remember, in my graph, I fit a curve, but notice that the blues are low and the reds are higher. The blues are lower and the reds are higher. Adding in year may be beneficial. Maybe if I showed you this graph with the years displayed, well, let's even hover over at row 1, row 12, row 35. You can even see which data point it is, and I'm spotting that we have the lower values for year with lower row numbers downstairs, and then upstairs it's on average higher row numbers. So let's go ahead and do that analysis with Fit Model. Okay, again, maybe the year should be incorporated. I'm going to have rainfall level, And I'm going to take rainfall level, highlight that, and under macros, say polynomial to degree 2, have rainfall squared in my model, all to predict the yield. Okay, over here we get a lot of output, and highlighting the things that seem most beneficial to emphasize. I'm able to explain some 40% of the variability. Now, that's without an interaction term. I've got rainfall, rainfall squared, and yield, all highly significant individually in terms of their slopes. The effects test, same thing as slopes, very noticeable relationships. The model overall is explaining something. Let's see how our model works out with our factor profiler. The factor profiler shows that curve pattern relating rainfall level to the yield. Maybe we should make this larger so we can see it more easily. So definitely a curvilinear pattern. There's no straight horizontal line that would fall into this gray zone. So there's noticeable curvature in our fit model. And that's true whether it's early on, 1890, or later on, even 1928 or 27 or so, that we had in our data set. Okay, I'm spotting one thing here. Notice that this rainfall arc, which has sort of an optimal rainfall level, it seems like, notice that it is the same shape exactly. Just that black trend line, not the curves of close enough to truth around the trend line, just the black line itself in the center. Notice that it remains parallel to itself as I slide it downwards for earlier years. Just the black trend line is identical in terms of its curvature, yeah? The reason is there is no interaction between the curvature term, the slope of rainfall squared, with the year. So how do you think we could adjust that if we believe that maybe the nature of the curvature were allowed to vary across the years? So not seeing any of the 5 of you raising your hands and flagging me down here, I'll say, what about an interaction? If you have a slope, yeah, and you want that slope to differ across the years, shouldn't the slope of rainfall be dependent on the year? Having an interaction between rainfall and year should do it. Okay, let's go ahead and take our friend, fit model, recall. Now add in an interaction between year and rainfall itself. Highlight them both, cross that. Now this interaction, it's making the model even more complex. Yield depends on the year. Well, shoot, technology happens. Rainfall, well, plants, they depend on water, but too much water is bad. The too much water is bad thing here is in the rainfall squared term because it says there is a maximum, and then after that it's a downward trend. Too much water is bad for you. The year rainfall interaction is saying this slope of rainfall may differ across the years. Now, for some of you, you may or may not be really comfortable with this, but y'all remember completing the square back in high school? You remember the term completing the square. Okay, so if you remember the term completing the square, you might be willing to buy the argument that if I have the something times x changed, I'm effectively changing the central location of the quadratic. The quadratic, if this rainfall year interaction is statistically significant, it's saying that the bottom or the top of the arc is going to be changing its location. Different rainfall levels may be optimal for different years. Here's my quick argument for why that might make sense. Okay, again, crop history here. Before the Weather Channel, if it had been dry for 3 weeks running, don't you think you'd be tempted to put a lot of rain, or I guess irrigation water on your crop? Yeah, and then if the rainfall comes in and it's a deluge, would you have just killed your crop from your earlier choice? So I'm arguing that perhaps just due to the lack of information that we currently would have, but back in the day they would not have had, the optimum amount of rainfall for a year, which nowadays I don't even know that we would have one, because you just irrigate whatever water level you want. You're going to get that unless you get natural rain that's so much that it kills your crop. Now we're going to be able to forecast out a week or 2 or 3 and at least be able to make wise irrigation choices in the next couple weeks. Back then in the 1900s, early 1900s, we would not have had that choice. And so perhaps the maximum value, the peak of that quadratic, is going to be different across the different years. The year rainfall interaction would allow for that to happen. Running the analysis. And I'm going to just jump right down to 3 things. One is, does r squared go up? 57. I guess that's a good thing. The interaction of year and rainfall, even if rainfall squared is in the model, it is helping me. So that's a good thing. The effects test for 1 degree of freedom terms, like in the parameter estimate section, these are testing for slopes. Okay, so the effects test would have the exact same p-value. Let's then focus now on our profiler. Under factor profiling, we can come to terms with what is going on and maybe make it bigger so I could read it more easily. Okay, notice that the peak here is at about 13 inches of rainfall. Okay, in 1890, would the peak have been in a different location than 13 inches of rainfall? And then as you go back further in time, forward in time, the peak rainfall or optimal rainfall level is going to be lower. And again, that's for a reason that I would argue makes sense, because if you have some natural rain, but not too much, you're going to be able to add irrigation water and you'll never end up drowning your crop. Earlier on, before irrigation was quite as prominent, you would say, well, there is a optimal, okay, and very, very, very early on, you were likely to say more rain is good, we're happy with that no matter what. Okay, that's if we have an interaction with rainfall level and then year, have rainfall and year individually in our model, but notice that we don't have a rainfall squared times year interaction term. What would a rainfall squared times year interaction? That means the slope of rainfall squared, if you will, the curvature term. The curvature term is negative 0.18. If it becomes negative even more, it's going to make it even more curved. If it becomes smaller, it's going to be flattened out. If the curvature If it's not just centered at different places, but if the curvature is going to be very, very cone-like versus very arch-like versus very flat, like barely a rise and barely a fall, okay, that interaction of rainfall squared with year could be incorporated into our model. And I'm looking at like 6 of you are saying, do it. Just because you want to say, will it be significant? I mean, what the heck? I don't even know how to easily grab onto all of this other than via the crop science history. But if it is significant, you should think about it in your disciplinary understanding. I'm only bringing this example to you because, to be honest, it's hard. And you all can relate to growing things, or at least you've driven by a field. I shouldn't maybe assume that. If any of you are, well, actually, Cal Poly has fields. You've driven by a field sometime. Okay, so you can imagine a plant even if you don't live and breathe plants. Okay, but in your own discipline, if you have these higher order interaction terms, it becomes challenging to understand what it is, how to make sense of it. If I want rainfall squared times year, I could highlight rainfall squared, and I could highlight year and hit cross. Rainfall squared times year. And just for fun, let's see if it's statistically significant, whether R squared goes up, and let's look at the pictures, because you all want to do that. Or if you don't, well, you don't have to. You may close your eyes now. Okay, 57%. Was it dramatically better than before? 57% and 57% are about the same. Hey, what about this rainfall times year? No need for it at all. The curvature that we do see is not changing across the years. Maybe it's centered at a different place. Maybe, if you will, the slope is changing. Those are the same statement. But the nature of the curvature is not noticeably changing over time. Okay, so that's a lot of content, which if you don't know crops history, well, hopefully we're able to at least tell you a good story that would justify each of these things. Okay, do any of you want to ask questions about that? I've noticed that perhaps I've been going quickly because y'all as a group have been quieter than average. Okay, so what I would like you to do as a favor to me is between now and next time, look through the content in Chapter 7 on interactions between quantitative variables. Perhaps watch this again. Look at also quadratics or self-interactions and raise questions. Next time at the beginning of class, I will also put online for you a sample exam for the next test. And if you would like me to, next time we can start with another example along these lines, maybe not as intense, but also one that you can all perhaps relate to. Or if you'd like to, we could move into Chapter 8 content and Chapter 9 content. Again, also benefits your understanding of the material that will be on the exam, but it is not specifically going to be tested on the exam. So any last questions administratively before we call it a day? Okay, that is it. So I'm going to stop recording, and I will encourage you to enjoy the rest of your day. And if you click out, that's fine. And if you stay here, I'll be here until 2 o'clock.